I'm glad to be here to see so many familiar faces, some old-time friends, some new people. Um, so let me share the screen to start. Just before I start with that, as you know, my name is Javier. People call me Pocho. And here is my accompanying mate, because I live in Buenos Aires, and here we drink mate all the time. So for the people that was curious, this is just a kind of tea from the south part of the planet. Okay, so let me share the screen. Great. Let me know if there's any problem or something. I think you should be seeing my screen. And okay, so how do I close this? Well, so what I'm going to talk about today is something called lib metacircular runtimes, which I have talked about in the past. So you might see that this talk is familiar to you. Maybe the slides are familiar. I usually evolve them, so you will see that they look very much like previous ones in previous presentation, if you ever saw a talk that I gave before, but they are always evolving, so I hope they will be interesting. And in particular, I'm going to show a little bit more of the work we are doing on Egg, which will be like the second stage of lib metacircular runtimes, or the second implementation. And before that, before showing Egg, so I will talk about lib metacircular runtimes. I'm doing a PhD here in Buenos Aires University related to that, to lib metacircular runtimes. I'm hopefully finishing it very soon, TM. And meanwhile, I also work for Labware and for Quorum Software. And the work in lib metacircular runtimes started in Quorum, so I'm going to give you a glimpse of what they do there. So basically, what we do in Quorum, or what I do in Quorum, is to work in a Smalltalk system called B that sustains this PetroVR software, which is a simulation tool for the oil and gas industry. So PetroVR is implemented in Smalltalk. It does all kind of crazy simulations about projects of oil and gas, and all of that is implemented in Smalltalk, and in particular, it's implemented in B Smalltalk. So my work there is to maintain the B Smalltalk core libraries and VM. And what's the problem with that, right? And how does that work? So when I presented this topic for the first time, I was presenting it for a non-Smalltalk audience. So maybe if you feel like this is too generic, you can tell me, but I think it won't be. So I will first talk a little bit about PMs and the problem that the team faced when implementing PetroVR. And then I'm going to talk about how we solve that. And after that, I will talk about Egg. So that's the plan. So what was the insight that we had, or the problem that we had? Okay, so let's go a little bit back in history, right? So you probably many of you know the history. I know the Bark history back in the 70s. There were a lot of people doing computer software, but with this focus in epistemology, right? So there were people working and developing their theories about how we understand and how we acquire knowledge, how we can build systems that let us create new ideas in our head, and how we can do that by building things, and how we can augment the human intellect and many other things. So the basic idea is that they were asking themselves how we can think better. And well, basically they decided, they created a lot of things to be able to think better, right? So they designed basically object-oriented programming platforms. Basically, we now have a lot of object-oriented programming platforms. The most well-known are, well, of course, Python, Ruby, JavaScript, Java. This is something that most people see every day. But we also have Lisp systems. We also have Smalltalk. And well, what was the benefit of these kind of platforms? How can they help us think better, right? The thing is that they have nice features and they have some properties which are nice, right? Well, basically, we can think about message passing. They collect garbage. They provide a lot of assistance, like being able to encapsulate code, to have to share implementations, to reuse code, to interact quickly. They have a lot of properties which are nice and that let us think better. But what's the problem? Well, the problem is that usually developers don't need to know how these features are implemented, right? But sometimes they don't work. And what's the problem with that? Well, so here is kind of meme or joke about that. Basically, when there's a problem with the VM, you have to call somebody else, because else nobody knows how to fix it, and nobody knows what actually are the pieces and the parts of the VM. And so how are typically this object-oriented programming language is designed? Well, basically, you have this high-level layer where you write your application, and then you have your virtual machine that will provide you some features and will let you abstract your code so that you don't have to think about the hardware and the operating system. So you can have, for example, application developers writing an application like PetroVR, virtual machine developers like me developing the core, the system, and the VM, right? So your VM might have garbage collection, JIT compilation, primitives, whatever. So application developers don't really know how the primitives work, how the GC work, how the JIT compiler works. So when there's a problem, they go and call the VM devs and ask them for help. And well, the problem is that sometimes you can't call the developers, or you want to understand better how the VM works. And let's see what languages are used to implement most known VMs, right? So, for example, in Python, you have CPython. It's written in C++ and C. The same for Ruby. The main VM of Ruby, C-Ruby, is written in C++. The same happens for most well-known JavaScript implementations. V8 is the one for Chrome, SpiderMonkey for Firefox, JavaScript Core for the Apple version. All are written in C++. You have the same for Java for the main VM, Hotspot. And you also have another implementation of Java, which is written in Java. So it's a kind of metacircular implementation. And while I'm not a really an expert in Lisp. Actually, I know very little in Lisp. Well, you have implementations for Lisp also, as far as you know, written in parts in Lisp and parts in C, right? So they all mostly do the same. And in the case of Open Smalltalk, the VM that we use for basically Squeak, Pharo, and Quiz, well, the VM is implemented in Slang, which is like a cut down version of Smalltalk. But that Smalltalk is translated to C or transpiled to C and then compiled. So the VM is actually built as a binary. Our original VM for B was written in C++, and our new lib Metacircular Runtime is written in Smalltalk, and we are going to talk about a little bit of that. So to understand the kind of problem we are dealing with, let's see how big these VMs are, right? They are quite big, millions of lines of code, and basically understanding these VMs is very difficult. I mean, teams of dozens and hundreds of engineers to work on the VM, and people using all those VMs and knowing nothing about how they work. So that might be a problem. So what what other people has tried when trying to deal with this problem of trying to simplify access to the VM, well, they have implemented different kinds of designs, right? So, for example, in the case of Open Smalltalk VM and also in Jaix VM, which is a Java in Java VM, they have augmented the semantics of the language, so that the language can access some kind of interesting objects or parts of objects from the language, but they still separating what is the application and what is the VM. You usually run a compiled VM, and you might, for example, simulate the VM and have it simulated for a while, but usually the VM is already built as a static thing. And these augmented semantics are gone when you are running your code. There's also another approach, which is called free, fully reflective execution environments. And well, it's a similar idea, but in this case, the idea is to present an API from the point of view of the virtual machine, which lets you change the way in which you read and write fields in objects, or how you can implement lookup. So you can alter the way in which the virtual machine behaves. But again, this is completely static in the way that you write it beforehand, you compile your VM, and then your developers can configure your VM by basically accessing that API, but they cannot change what the API has. There's another approach, which is called first-class interpreters. There was this little team, I think it was in RMod, like 15 years ago, that they were writing this first-class interpreter, which basically means that you can write an interpreter in high level and you can modify it. So you can make your VM behave in different ways by changing your interpreter. The main drawback that it had was that, well, while the interpreter is there, you also have to have a proper functioning virtual machine behind, so that what you change from the interpreter is not that much, it's still a little bit static, and it's not thought to be very performant. At least that was what they were able to build at that time. And of course, again, there's this kind of separation between what is supposed to be done by app developers and what's supposed to be done by virtual machine developers. And so this is the hypothesis in my thesis. You can read it. It's going to be there when after the slides are or this talk is recorded. But I can tell you what's the main idea. The idea is that we're building VMs because basically we want to abstract all the things that are related to hardware and to the operating system and all complexity that is beyond what the programmer is doing while writing their application. So we basically create this virtual machine, which is in another layer and that we cannot access. Well, but object-oriented programming languages already have tools for abstraction, for hiding complexity, and for other things like short feedback loops. And so if we were able to use those properties of the programming language for writing a virtual machine, then we would be basically having a design where we are using the same language for the VM than for the application, and where the developers can basically work with the VM as if they were working with the application. And well, that would basically make their lives better. That's the main idea. And so what we have done was to collect some case studies from the real life, from programming, or collected by application developers. So one of the key insights was that when we did this, we did it because we wanted to have better tools for VM development, for VM developers. But in the end, it showed up that it was also beneficial for application developers to have these kind of tools. So what we did, because it's very hard to determine that the system is better if basically if you are trying to just show that somebody likes it more or not. Well, that's not a very scientific way of proving anything. So what we did instead, because doing studies with people is very hard, because well, you would need a lot of VM developers being willing to do these kind of studies. We did a qualitative analysis and quantitative analysis of these 3 case studies. When somebody programming their application has to deal with these 3 problems, and what would be the things that would that are needed to be done when developing with a traditional VM written in C++, and then we show how these problems can be solved with our approach. And we show that actually there are much less tasks to perform, so that basically the system is better in that it requires much less effort from the programmer to solve these problems, and that they can do it in a shorter time. So these 3 case studies were basically trying to make the system do faster garbage collection by tuning some parameters and basically modifying the code a little bit of the garbage collector, because basically, as the garbage collector is written in Smalltalk, it's quite easy to access the code from the point of view of the programmer, and to change some line here or there that will change the way in which the garbage collector chooses sizes for things like for like the space, the areas of memory that is going to be used, or things like that. We also did some experiments, or took another use case where the programmer had to deal with some caching issues with the JIT compiler. And the final one is about letting programmers use SIMD instructions directly from their code, instead of trying to have support for the from the VM written by VM developers to be able to have that support. So that was our study. And so what's the main problem of developing VMs in the traditional way, where you have 2 layers? Basically, the main problem is that the view of the VM from the application developers is opaque. So the application developer doesn't know whether the VM is doing something good or bad, right or wrong. They just don't know. And so, as it's not possible to see what the VM is doing, well, basically app developers know nothing about the VM. So there is this gap between what they know about the application and what they know about the VM, and they actually usually don't even know how to download the VM code or how to compile it, less to change it. And then if they have to make a change to the VM, even if it's a very small, tiny change, well, that will take them a lot of time, because the feedback loop is quite long, because you have to download the code, which you don't know where it is. You have to compile it with tools that you don't usually use. Then you have to try to look where the connection is from the problem you have to the VM, which is not obvious, because the VM is sitting in a layer which from the outside is completely disconnected to the application. So again, it's very hard for application developers to become VM developers. So let's talk a little bit about the LMR. I don't know, up to now, if you have any questions, you can talk, you can ask, tell whatever you want, so that I don't feel I'm talking just alone here. I hope everybody's still listening there.
Still listening attentively.
Okay, I will keep talking then. But if you have any questions, you can just ask. So what else? So what was the idea of we leave metacircular runtimes? Well, basically, it's not that different to what you have in Open Smalltalk, because we programmed a garbage collector, a JIT compiler, and lookup in Smalltalk. But instead of transpiling that to C, we basically added some kind of semantics to the language too. And then basically just let the thing run. Okay, so you don't have to have a separate layer. We just applied object-oriented programming techniques like encapsulation, polymorphism, everything you already know about. And if we augment the semantics a little bit, and we add support for some kind of special messages to the language, then we can implement any part of the VM. That's basically the approach. And well, what's the gain of that? Well, basically that you get a first-class representation of the VM in the application, and the application, the VM becomes just another module or set of modules in your system, so you can browse it. So you lose all your, or not all, but you can lose much of your fear about what the VM is, because it's all there. Yeah, you can see it. And if there's connection from the application to the VM, you are going to usually just see it, because it's like you are going to see, for example, when you are running and you have a performance problem, you are going to see in a profile just that maybe your garbage collection methods are showing up much more than you expected, or maybe it's the JIT compiler, things like that. But you're going to be able to basically browse the code and understand it because it's there. And that's the nice thing. And so your knowledge gap becomes much smaller. And then you can try actually to say, okay, but if this is just doing this thing, let's try it. Let's try to change it to some other thing. And well, it's just like anything in Smalltalk, you just change method and it gets applied immediately. So basically the feedback loop is the time it takes you to find some code and write something else and accept it. That doesn't mean everything is perfect. I'm going to talk about that a little bit later, but it's an interesting experiment. So we call this thing a lib metacircular runtime, a lib metacircular virtual machine, and all aspects of the execution are modeled in Smalltalk, or at least much more than before. It's made of basically 3 modules, one to write what usually are the primitives, one extra module for the JIT compiler, and finally one other module for the garbage collectors. And all of that can be lightly programmed. Well, so I'm not going to demo right now. I just saved some screenshots. I have demoed this before in some conferences. I think it was in Toronto or something like that, and I have shown many parts of the system. I will show more about Egg. So I wanted to show more about Egg than this, which is something that I've shown before. So I'm not going to demo this. I haven't prepared anything in particular. But anyway, you can see here, this is a typical cross browser, and it's just showing a garbage collector class that has some Smalltalk methods, and basically all the code of the garbage collector is written in Smalltalk. And you can, for example, access the instance of the garbage collector that is running, or the heap that is running, and you can ask it, for example, for some statistics about what it's been doing, and what were like what we can see here in this inspector is like each pass basically stored some statistics about how much it took to run the GC, how much it collected, how much it tenured, what was the reservable rate, and the size of the remember set, and all kinds of things. So you can, for example, access that object, which is a collection of statistics, and you can create a chart for that, and then you can draw whatever you want. So you can understand your system in a way where, like, what you are used for any. This is kind of exploratory environment for VM, where it used to be an exploratory environment for anything else, and that's the idea. You can also debug things like the JIT compiler. Just you, what we see here is, for example, I said, okay, let's halt when we are compiling or JIT compiling foo method, or some method that has the selector foo. And you can just basically do step-by-step debugging of that method, so you can see what it does when it has to nativize or create native code for this particular method. Okay, so for that we did after that we did a qualitative evaluation of our case studies and compared it to the other systems. I'm not sure how much interest is in this, so I'm going to just explain it very quickly. Basically, the kind of representation that we have of the VM is very object-oriented in V, and the correspondence from the code of the application and to the code of the VM is quite immediate, because you can see it if you stop the system at some point, you halt it with alt dot or whatever, you are going to see what's going on. And allows for exploratory programming, as I was showing, and shortened the knowledge gap quite a bit compared to traditional VMs. And then different kind of VMs are very, let's say, fast, are optimized a lot. They perform very well, but they cannot do these kind of things, and the application developers don't really know how they are made. So it's very hard to do VM programming. Some of them allows, for example, for a smaller knowledge gap, like in JAX, because it's Java done in Java. So, well, you already know Java, but if you're programming in Java, but there's not much dynamism there. Other environments have this kind of more dynamism, or allow for better understanding of the system, but they still keep the separation of what is the VM and what is the application. And usually you have some kind of simulation of what the VM is, or simulation of the VM to understand better the system, but it's not what developers usually are running. So you still have this kind of, yeah, you can have a first class representation of the VM, but it's not what is used every day. And for performance, we also did some we did some quantitative evaluation, like what's the size of the system. The system is quite small, 22,000 lines of code for the whole system. And we also basically tried it with the ArgWeFast benchmarks. I think most people know these benchmarks. These are benchmarks for VMs, basically. You can check whether your language implementation runs faster or slower than other language implementation. The benchmarks are written in a way which is quite abstract, so that they are not trying to optimize the benchmarks or the solution for the benchmarks in any way. They just write them in a way where the VM has to do all of the work of optimization. So what we can see here is that, well, Node.js is our kind of faster system. So if a benchmark takes 1 in Node.js, it takes between 3 and let's say 6-7 times slower in Pharo. And here we have V, a little bit slower, and then we have Ruby and Python, which is quite slow. But these are quite conservative tests. I've seen this move a little bit to this side. So this is not limit. This is actually to prove as a lower boundary and not higher boundary. So I think we can make the system write quite faster. But it's just to show that this kind of system don't have to be slow. there's no no barrier for making them fast enough first, because they run already much faster than other systems which are used every day by a lot of people. And we can also, and I have many ideas. If people is interested, I can tell how to make all this much faster and go to this side. So some concerns. Well, first of all, we are letting people write the VM. So are we make the VM, which was not safe, even less safe? Well, we are not sure, because in Smalltalk is a very unsafe system in that in the dimension of letting the programmer do whatever they want. So I think that when a system is so unsafe, there's not much you can do. I mean, you cannot make it worse, because it was already very unsafe. But it's a concern, and there are other ways to make these kind of systems safer. Gila has shown us a way. So I guess we could try to, if interested, we could try to make something along the lines of mirrors and things like that to make the system safer. Well, there's also the stability problem, like you're doing brain surgery to yourself, so you're going to crash your system, you're going to break everything. Well, we already proved, or we have already been shown that having classes and meta classes in the system can be a concern, but in practice it isn't, because you can just change them and change methods and change everything, and you can make your system solid, and that won't be a problem. So you can save the image before doing a big change. You can change one system from the outside to be able to do bigger changes and things like that. So that's really not that a big problem. Well, some paper reviewers were also concerned about dynamicity, like, well, what can you do with these kind of systems? Can you, for example, make read-only objects, or change something in the system in ways that were not thought of before? Well, the answer to that is that we are not making a super dynamic system in that sense. So we are not trying to let programmers change everything while they are alive. This is not for that. This implementation doesn't solve that problem. If you want to have read-only objects, well, you might be able to use free header bits in your system, so it might help you, but won't help you in other problems. Like if you want to change all the header of an object to some other new shape, well, you will probably have to reboot your system. It's not that dynamic. You will have to modify things with your system running in kind of spec mode, where the system is not really running, and change the files and then create a new image. So it's not supposed to do that. And well, another question was, how do you debug the system when you crash it? And basically, we can. The answer for that is that we can have some extra tool, which is the native debugger, that allows you to look at the memory of the system from the outside, have the system completely stop, and look at the stack, look at the objects. We designed the framework for dealing with that. Usually it's not that a big problem, because also when you are programming, you can design the different parts of the system in a way where you can work with them without using them at the same time. Like if you want to do, I don't know, a change to the JIT compiler, you can test it, for example, for some particular case in a separate environment. so you don't have to use it while it's running if it's very, very, very unsafe to do that. So you can manage your safetiness. So you can check where you are doing something very unsafe, so you are going to use some different tool, or if you are doing something which is not supposed to be very unsafe, then you can just save the image and try it and see how it goes. Okay, so what's next? This is the evolution of V, right? So I'm going to introduce Egg. I don't know if you want to ask anything about all this before I start with the Egg, or as you wish.
I have lots of things to ask, but I don't want to derail the whole sequence. There's several points here. One is this business of stability and what if it crashes and so forth. So you've alluded to this, but you can set up systems so that you are essentially using Smalltalky tools to manage a distinct process or image or whatever. If you're the more your system uses mirrors for reflection, the easier it is to do that. You sort of are hinting at that, but do you want to say a bit more about that?
Yeah, well, we have basically created a tool that is like a native debugger that halts the system from the outside, and then by looking at the memory, allows you to access the objects using different representations. One of them are mirrors, so you can, for example, obtain a compile method mirror or a class mirror, things like that, so that you can inspect the instances which are there, or is maybe a stack frame mirror, things like that. And we have also tried another possibilities, which are, for example, what is described in a paper called Metaphysics. Basically, we have this kind of proxies that have a reference to the object ID on the remote side, and then have a reference to an object that says how this remote object should be treated. So depending on what you want to do with this remote object, you may want to, for example, send it a message to the remote object, right? But what should that message do? Should it be executed on the other side, or should it be executed locally? And these kind of things can be changed by taking these proxies and attaching them different kinds of policies. So you can, for example, take an object and ask it for something, and the policy will make, when this proxy receives the message, will make the execution of that message be local by using the code of the image that is in the remote side, or with a different policy, you can make it execute with the code of the local image. And you can try different things depending on the case. You can even, while simulating the execution, because in the end it's like an interpreter of the code that is living in the remote side. You might find yourself that you need to create new objects to execute this message that was sent initially. Like you ask for you sent new to order collection, so that needs to create an object. So this new order collection will be created in the local side, not in the remote one. So you can have these proxies also for local objects, and you can have them work together. It's a little bit slow. We haven't tested like a proper measuring of how slow that was, but it's helpful in some cases where you want to have your system which is freezed on the other side. You want to send a message to some object and see what it responds. Usually small queries and things that could be answered very quickly without a lot of computation. You can just send the message to the proxy, and the proxy will execute it locally using the code of on the other side, which might be, for example, grabbed by a mirror. So you can use a mirror to get the compile method and then execute DST locally using these proxies. There are many variations possible.
Well, thanks. So I'll just shut up now.
Okay, so if there's no more questions, let's go to the next step, right? So Egg, first question, why another new Smalltalk? And well, there's supposed to be an answer for that. So that's what I have in mind, right? So the desktop devices where Smalltalk is running nowadays were just supposed to be an interim Dynabook, right? So we were, it's like we were supposed to drop all these desktop devices long ago, but we haven't. And now we are very used to them, but it's actually not what they were supposed to be, like the system where we should be working. For example, and actually nowadays the desktop devices are used by programmers and by many other use cases, but actually most people is using mobile phones for accessing the web and for accessing applications. And also many applications are written in a way where they run inside a browser. So there are also other things like IoT devices that can bring you a mate from one place to the other, and you have to program them. So everything has software inside. Of course, there are also lots of code running on high performance clusters or in the cloud. Basically, you have software running everywhere, and the Smalltalks we have were still thought to be used in desktop environments. So I think there's some kind of unoptimal situation where you are used to work with a system which is quite big. You have your development environment inside. You have a lot of things loaded there. And usually, well, you have to you need to have an adaptable system where you start from small and you make it grow. So usually, or what we have in mind, and one thing that we started doing in B, but not so fundamentally, was to start from a small kernel and then load things. But we wanted to write something where you could make this a no-brainer, so that you will write your modules, you will tell what are your dependencies, and the system should be able to load all that in a second and run. So basically, one of the things that Egg has that B doesn't, and that most of the Smalltalks I've tried doesn't have, is a module system. We are not trying to create like the Smalltalk of the very, very long future. It's just a Smalltalk that is modular enough, like to compete with systems that run every day, right? We are not trying to make something very, very radical or something that is super super good. We are trying to get something that is good enough for our cases. So in the case of Egg, you will have module objects, and module objects will have this imports method where they can say that they import something from some other module. And basically, well, actually, well, here we should have a hashtag because it's a symbol. But anyway, so the module tells what's going to import, and then it just has some code that uses those objects. So there's no Smalltalk global here anymore. That's one of the main differences, right? And well, as we shall see right now, these kind of things require a little bit of special tricks. Because, well, how do you load a module that references things which are not in the module? So for that, we implemented late bound names. Basically, when you want to load the module, if the module has references to other things, well, the code will have references to other things, and the compiler has to be able to deal with those names and not break in the way, right? So let's go for an example. If we want to load the module that has this method, we can see that temp is a temporary variable, but what is bus and what is bar? Usually, Smalltalk compilers try to optimize this access, and basically they create, when accessing bus variable, maybe that's an instance variable, so they will create a special bytecode, or they will output a bytecode for accessing an instance variable, and the other one might be a global variable in the Smalltalk dictionary, so it would be an association bytecode where it will read an association that is stored in the Smalltalk dictionary. So the idea is that in Egg, you don't have these kind of things, but you can work anyway. Basically, in Egg, everything but temps and arguments is dynamic. So you can do this kind of thing. You can write this method, you can load the module, it will compile the code, and what would be the bytecode for that would be just an access to an identifier, and the identifier won't be bound to that variable until the code is executed. In the moment where the code is executed for the first time, it will associate that identifier with a variable, and when binding that identifier with the variable, is going to cache the result of the lookup for that identifier, and it will use it the next time. So the next time it accesses that variable, it's going to be fast, and it won't have to do all the lookup again. So it's kind of a dynamic lookup for methods, but this time for instance variables, or for not only instance variables, for any kind of variables. And now one other difference that we made was that we created namespaces. So each module has its own namespace. So you cannot access objects outside the namespace unless you import them from somewhere else. And what else? Class variables and pool variables can be implemented using namespaces. So we don't have a special thing for class variables and pools. They're just basically namespaces. And what else? Well, I think that's it. That's one of the most different things from Egg to B and other systems. Okay, so let's go to the last part, which is the implementation details. So first of all of what Egg is already open source. It has been open source for some time. We have renamed this project. We baptized it Egg first year, and since then we have still been working on it. So well, by the end of the talk, you can see the link below. It's github.com/powerlang-egg. There is the repo. What you have in the repo is basically this. You have a modules directory where you can find basically the kernel and some other modules. And you have the runtimes because all those modules are written in Smalltalk in a format called tunnel, which probably most of you know. It's just a format in which you can write each class in a file and output all the code there. And well, then you need to execute it. So we have different VMs for different use cases. The first VM we wrote, we wanted it to have to be developed in an open source environment. So we used Pharo to write an interpreter for Egg and a bootstrapper. Then we worked on a JavaScript interpreter, or sorry, an Egg interpreter that runs on top of JavaScript. So you can use Egg in a web browser or in Node.js. I have also been working on the on a CPP or C++ interpreter for the non-believers, for people that doesn't believe in having LMRs. We can also give them a C++ traditional VM. And of course, there's also, well, inside here, you will also find the LMR version, but I will talk about that. That's pre-alpha state because there are many things to do here. So unlike B, A runs or is was created to be able to run on any platform, right? So we wanted to run on Linux, on Windows, on web, on Mac, anything, right? So it's supposed to work on many different things. We usually develop it from I use Ubuntu, and I'm usually working on the JS and the Pharo interpreter versions. So it's actually not native. The CPP version I was working on was also for Linux, but it's supposed to be expanded to other platforms. And so let's move a little bit forward. So let's talk about an example of a module. The compiler is a module. So if you go to modules-compiler, you will find all the code of the compiler and one file for each class. And there's also one compiler module.st, which is a class that inherits from module and basically tells how to initialize the module. And if there's any kind of, let's say, access point to the module, then it can implement all the access from that module. So, for example, it will tell what classes are imported from the kernel, and it will tell what to do when the module is just loaded. And here we see, well, that imports a couple of things. It doesn't import many because some classes are imported by default. I don't have the list right now, but I think that if you say array new, you don't have to import it because it's already imported. Some classes you don't need them because they are already literal, like true, false, or whatever. You don't need to import them because you can use them or access them from literals. But for other things, you just import these these classes by naming them in the imports method. And here we see that we are creating this binding IDs in the last method. Free encoder initialize binding IDs, basically create some pools. And so what this does is to add a namespace and then fill that namespace with some values, add some keys, and then you can just use it. So what you see here in these two cases, recall IDs. Well, this is the name of the bytecodes in Egg. The bytecodes in Egg are representing basically a low-level ASC. So when you compile a method, the result of the compilation are some bytecodes that if you decode them, you will get a tree. So they are called tree codes. But anyway, what we see here is that this method, initialize tree code IDs, uses this variable tree code IDs that is not defined anywhere. But the compiler creates a bytecode for accessing the identifier tree code IDs. So the first time it's executed, well, it will try to find this name first in the class of the receiver. If it doesn't, then in all the hierarchy. Then, if it doesn't, it will try in the module. And if it doesn't, well, then it will send the message, which is does not know, which works a little bit like does not understand. So in this case, the tree code ID is going to be found because we are just adding it as a namespace, right? And then we are adding some things to the namespace. And finally here, again, this is going to be resolved at runtime. The first time this is run, it will do lookup for this identifier, and it will detect that this is a variable inside this tree code ID's namespace. It will bind it, and next time it will use that bound variable, unless somebody else basically overrides that value. So it in that case, the cache will be thrown, and unless somebody makes this cache to be cleaned, then it will use the optimized already bound version. So that's a little bit more about namespaces. And running the code. Okay, so to run this code is in files. So the first thing you have to do is to create an initial image from all that specification. So it's good to have a bootstrap process to be able to evolve the most important part of the systems, like the kernel. If you have an image where you cannot change the kernel, or it's very hard, then you won't evolve the kernel. So we have this bootstrap process that works from Pharo, and you can create new images from the source code. And the metaphor is that you are going to have a host system where everything is already working, and you are going to create this guest system. In this case, will be Egg, that will ask for help from the host system from time to time until it's completely working. And so in this case, or in our case, it would be the native Egg version that would be loaded by a C++ loader, and it would work with a VM that would do garbage collection or whatever. But in the case of Pharo, what we are doing is to create a virtual image inside Pharo. This virtual image contains all the objects of the Egg image. And now, okay, so this is a part of the half demo, half slides. So after cloning the repo, you can just say make runtime-pharo, and it will compile things, and it will show you this message. I'm going to try it. I haven't tried that much this, but let's say. So what did I have to do? Runtime-pharo. Okay, it's already okay, it's already built. But let's say here we have, it says to open Pharo Bootstrap image, run Pharo UI egg image. So and we get this. So what is all this? This is an image that has all egg packages. Let's say here it's in this package Powerlang. So in this package Powerlang core, we have what is basically the main representation of the evaluator that Egg uses to be able to execute code of Egg. We also have a representation of Egg objects, and Egg object has some kind of basic API. For example, heap objects will have a header instance variable, and so you have very tiny objects to represent each instance living in the virtual image. But let's see what we have here. Okay, so what can you do with this? Basically, first of all, you can from Pharo browse all these ring environment. This is the way in which this is library. Ring is a library which Pharo has to allow to browse the tunnel files from within the image. Right? It has some problems, but you can browse the image. So what we are seeing here is the specification of Egg inside Pharo. So this class browser is showing us the kernel module of Egg. It has Boolean, it has true, false, some other things. Some methods there. We can browse all that. But still, also one other thing I wanted to do is to also, because we don't use this ID that much. Let me check here. One thing we have is this IDE that we use for browsing not only Pharo, but also for browsing B and for browsing Egg. You can just, if you build your image, it should suggest you this code here already in the transcript. This image I'm using here is a little bit old, but what it does is to create, to download something which is called website. There's a warning here, you have to skip it. Don't pay much attention. That's because this is an old, very old Pharo version, Pharo 9, that we are using for Egg. But anyway, so this just downloaded website. And now what we can do is to start a web server. Right here. And let's see. Can I move this? Okay. So this is an instance of website running on a server in the web. You can also, you should be able in the very short future, be able to download it as a snap for Ubuntu or an MSI package. Here is another example. This is an application, an Electron application. So website client runs on Node.js. So we package that as an application, and you can just use it, and then you just connect to whatever image you want. The image needs to have a server, so you connect to that server running, and you put your name here, and that's enough. So what I've done here is to install the backend and to start the server. And now to connect, the instructions say connect to the client here. So let's put this here. And here we are. Yeah. So here we are connecting to Pharo. So one thing, let's say, one thing I wanted to show was well, I wanted to show a little bit of website, because I think this is the thing we are going to use for programming Egg in the future, because Egg doesn't have an IDE, and what we are going to do is to create a backend for Egg. We have one now. I'm going to show that in a few minutes. But the nice thing is that we can connect to the Pharo instance here, create a virtual image of Egg, and then we could connect to Egg. So anyway, there are some instructions for running some code. For example, here I have them here. So let's move them to the other side. I want to execute them here. So for example, I can execute this, and then I can just try this example. It will create a runtime, and then send plus to 3 and 4, and we can see the result. I don't know if this is running, so let's check. Okay, so it was running so quickly that I didn't see the result. So basically, what we have for the result is that the value of sending plus to 3 with the argument 4 is 7, right? So let's talk a little bit more about the bootstrap and how these are proto-egg objects. So the way in which we bootstrap Egg is basically building a basic image and then let it run. The first stage is basically building this kind of proto-egg objects. These objects are are a representation of the objects of egg, where the class of the objects is not the actual class in the way in which Smalltalk objects are created. For example, Smalltalk objects point to their class, and their class also has a class. So they all reference themselves in a metacircular way, or in a circular way. For the first stage in Egg, we make objects point to the specification, to this ring specification that knows the code of the objects from the files. And why do we do this? Because we can basically create the basic classes, but without filling their method dictionaries, without anything, and then we can use that basic image to execute code, and the code will be executed using the ring specification instead of the method dictionaries of objects that haven't been created yet. In the second stage, we basically take the resulting initialized image and we convert it to a metacircular image where after the first proto-egg objects are created, they are added the methods to their method dictionaries in this proto-image. And finally, we convert that when we have all the objects with all the method dictionaries and all the classes already working, the symbol set is already working, we switch or migrate them to this metacircular runtime where everything is in order, like in a traditional Smalltalk, and then let it run inside Pharo. So again, to be able to create this image, let's copy this. Here. We are going to basically create this image for 64 bits, generate the basic objects that the Genesis Bootstrap will initialize the very basic initialization. Then we are going to fill the classes with the methods in the method dictionaries. Then we are going to also add all the systems, all the symbols that we have used to the symbol set. And then we are going to pass to this second stage, where from this ring image or image in stage 1, we are going to migrate to a metacircular image or an image of the stage 2. And then we are just again going to send some message to the result and show it in the transcript. So again, let's play this. It's executing. We shall see this. I think that it's not going to show up here because I should connect the transcript from Pharo to this website image. I think that it's actually going to be shown here if I open a transcript. Yeah. So again, this time what it was doing was sending the message name to the object kernel, which is a normal object of type module, and it was showing that name in the transcript, right? So the name of the module is kernel. If we inspect this, so this is an egg byte object, which is just a string, right? So let's go back a little bit to the presentation so that I don't take all of the time. So this is the Pharo VM, right? This is just one way in which we can use Egg. You can see this is like a toy Egg version, where we are just creating a kernel and being able to send some messages. And we are not planning to be using it for many things, but just for maybe modifying the kernel and checking whether it works or not, or things like that. So what else can we do? Okay, we can do, for example, we also have a JavaScript VM. I have shown this a little bit in previous talks. I think it was in the past Smalltalks. So we have a JavaScript or an Egg implementation that runs on top of JavaScript. Again, so Egg is a Smalltalk system that is aimed to or targeted to different platforms, and all the code should work the same in each platform as long as the platform allows, right? If you are running on native, maybe, well, you are going to be able to do some more things than if running on JS, because in JS, that's a sandbox environment, so you can do less. But anyway, the code that you're going to use should be the same and do exactly the same thing. So in the case of the JS version, instead of writing another VM or another interpreter, we transpiled the Pharo version of the Egg interpreter to JavaScript. And instead of writing the bootstrapper for Egg in JavaScript, we instead generate an image in Pharo using the Egg Pharo bootstrapper, and then write that into a JSON file that the JavaScript runtime can read. So what does the transpilation step look like? Basically, if we have this Egg object class and we subclass Egg object with this instance variable, we have a JavaScript file that takes the Egg object class and creates a subclass in JavaScript. And it's quite straightforward to generate JavaScript code for this Smalltalk code. We can also then take each method and transpile that. So for example, here we have some code of the VM in Pharo and the resulting code in JavaScript. So we can transpile all the VM code. And the interesting thing is that we are not going to transpile the application code of Egg from Pharo to JavaScript. We are only transpiling the VM. So the code of the modules shall run exactly the same in Pharo and in JavaScript. It's only the VM that is transpiled in a controlled way in which we know that it works well. And all that it does, the interpreter is going to do the same in Pharo and in JavaScript. We had to add some glue code there. For example, when transpiling, if somebody asks if nil to an object of any type, it has to be able to respond that. I'm going to skip this because we're already getting short of time. But we can add some glue code for the VM to work well in the JavaScript environment. And what we are doing next is to generate a kernel segment from the image that we have in Pharo. So let's try to put all the pieces together. Here we have, let's look at the files. Here we have the modules here and the runtime here. In the modules, we have the kernel module with all of its files. It's just files, it's dev files. So you cannot do much with that. You have to generate an image. So we use Pharo to create a virtual image, something like this. Bring image, and then we can send messages to the image that is living there. Then, what can we do with that? We can send a message to the image to tell it to write the kernel module and all of its contents as an image segment, as a binary file that will be read by the JavaScript engine. So let's go back here. We tell the transpiler to generate the kernel segment. And to generate the kernel segment, it will write an image segment of type JSON. So if we go back here, we have this image segment builder module that is able to take an image, to take a module and to generate a JSON-based file that has the contents of all the module. All the objects there are serialized in a JSON format. And the result let's go here to the JS image segments, is written here as some kind of JSON. This is an object table. This resulting image segment is basically an object table with some exports in a format that the JavaScript engine can read and access. So the kernel module doesn't have any import because it's self-sustained, and it exports some objects. So again, let's go back here. After writing that JSON, our example server is going to basically import a loader that knows how to read that JSON and to create an image from that. It will tell it to load the kernel file, to load some core modules, and finally it's going to start a website server that will answer questions about the objects living in that image so that we can browse it. Let's do this. Let's run this. So let's now go to the example server. Here, okay. We can run it here, I guess. Oh, it's already on, but let's run it again. So we are running this on JavaScript on a Node.js instance. It's going to basically load the kernel, load some modules, and then let us access it at this address. So again, we go back here. I think we can duplicate this. And now we are connected to Egg. So this is the Egg image that was read by the Node server, and we can browse it. And now it's going to show all the things. Well, there can be some problems here and there, but it's going to show all the things that we were already seeing back in the Pharo image using this. But while this is only showing the specification, like there are no live instances of anything. Here we are connected to a real image working inside the node server that is running here. So we can tell, for example, again, let's see if expressions work. I'm not sure if I haven't prepared this for the demo, so I'm not sure if it will work. Doesn't look like it's going to work. No. No, it's not working. So I'm not going to try to make it work. But well, one thing I didn't show actually, but website is being used for working with B every day. So it has lots of features. Guillermo is going to show this in the I think he's going to show this in ISA. I'm not sure, but there are a lot of things you can do. There are so many things to show here. I won't even try because it's such a long list of things. But one thing that is very interesting of this is that website is two things. On one side, it's an IDE that will let you browse your image. In this case, we are browsing Pharo. You can browse Egg, you can browse whatever you want, as long as you create a backend for your Smalltalk. You can use website to browse your image. And the other interesting thing is that even if you don't like to have this working on a browser because it's not written in Smalltalk, well, you can use the API because website is also an API that defines how all the things work in the back to connect to the remote server. So you could, if you wanted, use the website API specification to write your own IDE in Smalltalk, and then you would be able to create to any other Smalltalk that implements a backend for websites. So it works in both ways. You can connect to any Smalltalk that has a backend, but if you write another front end, then you can connect to any other Smalltalk that has the backend. Let's try to hurry because it's already long. Okay. What else? Well, as I was saying, this is only in a branch. It's not really working. But it's thought for very small footprints, like running on RISC-V with 32 bits or ESP 32-bit devices. So I didn't want to make people think that the only way to run this is using a live metacircular runtime or some kind of crazy technique that is very novel and not that proof. So we are going to have this C++ VM, but it's not for much of the interest, but only for supporting typical workflows. And finally, running Egg in live metacircular runtime mode, it's still not possible because the code is there, but still hasn't been plugged in the way that Egg requires with all this modularity and all that. We have to do some changes before it can work with the LMR. So it's still not there. The code is mostly there, but if you try it, you won't get very far. Actually, there's no way to generate an image still for the LMR. So you can just browse the files and read the code, but not much more than that. And well, that was long talk. Thank you very much for this space, for showing all these ideas. Again, no, any questions that you have, please ask. I'll answer happily.
So I have lots of questions and comments and things. I don't want to hog the necessarily all the time, but briefly, so egg, what is setting aside the LMR stuff? The point of egg as opposed to B is this module thing, or what is the reason for not using B for all this?
Yeah, well, there are two things. One of them is modularity, and the other one is that it's supposed to work in many platforms, right? And well, there's an extra thing that we wanted to share to check some ideas. And so the thing is this, Petra VR is running on top of B. So we want to keep B very, very, very stable. And we want to have space for changing some stuff, right? So we said, okay, let's start with something afresh that shares most of the things of B that we can use, because B code has been also open source, but there was no bootstrapper. We started with a bootstrapper, and we said, well, but we want to change these things and these things from B. And we said, okay, but that's not going to be like the B we used to have. So let's just put it another name. Let's bring the things we are interested in from B to egg when we want, and let egg evolve as much as we want. But the main differences are that basically there's this module system that B doesn't have. This is well, this is open source from the start, and this is multi-platform, right? So those are the main differences there. From the implementation point of view, those are the main differences. From the philosophical point of view, is that we also wanted to experiment a little bit more. So the thing in the end was not what we had in the beginning. So we wanted to have a proper name for that.
Gotcha.
What's the level of work for so something like B, if other people wanted to experiment with the idea of modularizing some parts of the VM and writing those in Smalltalk, which seems pretty interesting to me and novel, and I hadn't seen stuff like that before. Like how much of the actual something like a Pharo VM needs to be changed to be able to load? Let's say, okay, now we're going to make the garbage collector be written in Smalltalk, or specifically just the JIT component, because that part's a little bit unclear. And then second part was about egg, which as mentions a couple of other things on top of it.
Yeah, well, it's we are not sure about that because we haven't tried to do that, so we don't know. What we know is that the whole LMR system, including GC, including the built-ins, and including the JIT compiler, is 22K lines of code. So that gives you an idea of how much code you would need to look up. Actually, the JIT was I don't know, I think it was in one of the slides that let's see here. So the JIT compiler is with the assembler is like the biggest part of the system. And well, the built-ins, this was meant for non-Smalltalk audience, so this particular table, but this is a primitives, right? So the first thing you would need would be to be able to make your primitives be replaced by these new primitives, and then to work in the JIT compiler. So how much work? I'm not sure. It's a little bit tricky because I think it has to be tailored to each VM. So you have to tailor your LMR implementation to your image or to what is expected from the VM. In this case, would be like the primitives that the Open Smalltalk VM has. Well, you have to replace them with these primitives written in Smalltalk. One interesting thing is that you don't have to make all work together at the same time. For example, you could load this JIT compiler code into your Pharo image, modulo all these incompatibilities between Smalltalks, right? But let's say that you were able to load this JIT compiler module, then you will be able to write assembly for the methods in Pharo. Then you can try to replace, for example, one primitive with a version that is generated dynamically using this JIT compiler. It's like a dynamic compiler that lets you generate native code. So you can start writing the primitives one by one in Smalltalk and replacing them with replacing the versions that your image has with the ones compiled dynamically. And if you need to modify the way in which the primitives are executed, because you have to be able to deal with the register calling convention and things like that, well, you can modify the JIT compiler to deal with that as long as much as you want, because it's just a Smalltalk code. So if the JIT compiler needs to generate code that saves, let's say, Rax register, then you can just modify that code and add some glue in the compiler that saves that register.
And it's a quick clarification, then B was not a part of the Pharo VM. It was like its own thing, or it is its own thing.
Yeah, B is not a part of the Pharo VM now.
Okay, thanks.
So if anyone else isn't asking questions, I'll continue. That's okay. So one of the things you mentioned early on was this augmented semantics. Is that extra primitives? What did you mean by augmented semantics for the LMR?
Okay, augmented semantics is actually where they are called under primitives. Let's see if we can show some code. It's basically statically bound messages. So let's see, for example, here. So here we have one example. This is a class. Critical array is just class, a kind of array that is used by this LMR thing. And it's basically an array that can grow, but is thought to be more performant than a classical order collection. So one of the things that you can do here is to ask, for example, for raw memory. So if you have this array that has this instance variable, the contents, you can ask the contents, for example, for some particular slot without any kind of bounds checking, at some particular index that you're interested in. So you just can access that slot. So how does this work? Well, basically this message, this particular message, is known by the JIT compiler. And when it sees this underscore basic add instead of sending a message, doing a traditional message send, it will generate the native instructions to access a slot at some particular index. So, for example, let's look. Well, I think we can look here for B. For example, I was telling you the basic add, right? So the basic add selector is implemented as a message. Well, here we have this method that tells the JIT compiler how to assemble the basic add. Instead of creating a message send when generating native code, it will basically take the argument, which is in some particular register, and convert it to a native integer, and then load the receiver at some address, which is at some address, and access it at the A offset, and finally store all that in the register R. So let's say we have a method that says we save this. The interesting thing is that because the system is dynamic, we can see what it does. So we can look, for example, at the disassembly. So here we have the compile method, right? But this compile method has some native code. And the native code, I should be using website for this, but I haven't set up the server. Anyway, so we have the two things here, or the three things.
Right. So this is basically like most Smalltalk compilers cheat on if true, and
Yeah,
there's a bunch of, you've just added a few more unclean.
yeah, exactly. But there's also another way. This was the first implementation, right? The first implementation was this. The second implementation is for the optimizing compiler, but the optimizing compiler is not like for every method. And this, I think it's not loaded. Let's see if I can load it. Oops, I think I broke everything because I don't have modules. I should have loaded this first. So you see, this is the kind of problems we have because we don't have modules in B. I think I broke the image.
That's okay. So I guess my next question was, if I took the 22,000 line LMR and converted it to Newspeak, and then changed it to deal with a few extra bytecodes or something so that I could compile Newspeak, how big a project do you think that is?
Well, I guess it's the same than for Pharo. I'm not sure. I would have to think about that. Actually, yeah, there wasn't so many people asking how much it would take to use this in this other language or that other language. It's a question I should answer.
So I have a good sense of what it takes to convert Smalltalk code to Newspeak code. That it's more like, okay, I need a few, I need to change the semantics a bit, right? Because I do not obviously I believe in my solution to the modularity problem, and that also actually will solve the security problem. So it's just a question of how hard do you think it is to do those semantic changes?
Well, I should check, because you also have to deal with the platform, because as this is native,
It's native x64, right?
yeah, it's native x64.
So
So
let's say we just worry about that, and we say it's going to be a native x64 newspeak that comes out of that, right?
that
So
works in Windows.
Yeah.
Okay. Well, you would need to basically port, I guess, the bytecodes and the primitives. I'm not sure how are primitives implemented in Newspeak.
Well, they've been done in different ways, often the wrong way. But there's not much that's different, except that there's a few bytecodes that are different. Really, you can get pretty far if you have the right bytecodes.
Okay. Well, we might check someday.
Anyway, we can worry about that offline, but that was kind of where I'm thinking, because as I'm sure you know, I think it's a shame that you are doing this improvised module system rather than doing it right. But
yeah, well, yeah, it's that's one of the things I wanted to say. Like, I know this is just an improvised module system, but still, it's better to have an improvised module system than having nothing, I think. Because you just saw how I broke my image because I didn't load the stuff in the correct order. It's much worse like that. So I just want to, I don't know, have something a little bit better than that. Not trying to make something the best, because I don't know. I think it would be like too far. I still want to keep the Smalltalk feeling of the thing, and so and we are facing some troubles, or not troubles, but some questions. Like here in Pharo, you can say, I don't know, let's say compiler, and you can inspect it, right? Or well, I don't know why it failed, but you can just use it. And here you have modules, but if you say here compiler, what's that? Because it doesn't know what the compiler is. So the developer is in an environment where this is supposed to be known, and it's we are still trying to answer ourselves what we want with that kind of things.
Yeah.
Just to chip in to, I think, Gilad, you are asking, is it impossible to like add Newspeak compiler, or I think it's more that how deep was your intake of breath? I wasn't detecting a large intake of breath at the challenge of adding a few bytecodes and implementing it. It sounded like it was doable as opposed to impossible, or perhaps not trivial, but I think maybe that kind of test is maybe the fairer one, not holding you to account here. But
you're asking Pocho, you're asking me what?
Yeah, I'm asking Javier, just sort of, is it impossible, or?
No. It's I think it's completely doable. It's just a matter of how much work does that need. I am not sure.
Like months instead of years, kind of thing.
Yeah, I don't know. No, I would say months, but
well, I mean, I think it was just that kind of general, obviously give or take, and we all know that sometimes estimates are wrong, but that felt reasonable, actually, like not impossible. That's pretty cool.
Yeah. I think it's pretty low.
Can I ask a quick question? You know, at the very end, when you ran the JavaScript version, and you said you ran the generated image segment, was that the transpiled VM that was running the image segment? That was the bit that I missed. Yeah, okay.
I can show the code there. So
it's just you said the script, and I wasn't sure. So that was the transpiled VM that you were executing then.
Yeah, that script is actually running this interpreter. And this interpreter was generated, all these files here were generated from the Pharo image. Right? So
okay,
yeah,
cool.
The only thing that we needed was, I think, to write in JavaScript was this thing that loads the file. And there is somewhere, I don't know where, there's, yeah, I think it's just this. Yeah, all the rest, besides the glue code, is here. So here's the keep object that I was showing.
Right.
One little optimization I did not long ago was that we had some performance problems with ifs, because if you see the code here, for example, let's check this method in Smalltalk, Boolean for in egg evaluator. Boolean for. So this returns, forget about the meaning, right? It just sends the message if true, if false to a Boolean. And this would normally be translated to something else because, oops. If you check here, this is an if clause that Smalltalk doesn't have. So the normal translation for this would be something like this. If true, if false, and then it would pass to lambdas, right? So it would be something like
okay.
Something like this, and the same for the if false part.
Mm-hmm.
But that's quite slow because, well, you are creating a lambda for each. I don't know if you have to do this. For each case, you are sending this message to a Boolean, and if you look at the glue code and look for if true, if false, you'll see that this is just an if, right? If this is true or this is false, evaluate one or the other closure. So this is quite slow. And what we implemented, or was it here? Yeah. What we implemented recently was an optimization phase that basically takes this message send in particular for if true, if false, and converts it to a JavaScript if then else clause, right? So it has to do some special trick because when you do an if else, then if that is being returned, well, you have to create a temporary variable, assign it in both branches, and then return that temporary variable. This is just nonsense from the transpiler, but so you have to do some transformation step to the JavaScript to basically modify the EST that you had before and to assign a little bit or some parts of the message. Like the last step in a block, you assign it to some temporary variable, and then you return that instead of the original message. The JavaScript compiler should be able to optimize all this, but the problem is that it has a budget. So if you give it too much things too many things to optimize, then it will empty its budget and won't optimize as much as you wanted. You cannot really tell it to optimize more, to use more budget. At least, I don't know if that's possible. I think not.
So your JavaScript transpiler, does it deal with things like proper handling of exceptions, like resumable exceptions? There's tons of issues if you
No, it doesn't, because it doesn't have to, because basically none of this code of the VM actually throws exceptions. And the exceptions in Smalltalk, well, they are just implemented using the Smalltalk object. So from the point of view of your application, the exceptions are just the same. You don't see any JavaScript treatment of exceptions.
Yeah, so you benefit from the fact that you know that you're only using the transpiler for very restricted code, so you don't have to deal with everything.
Exactly, yeah. That's the nice thing. And this was actually a hack because, well, you know, this if then else, who knows if it was going to be sent to a Boolean, right? Is it really going to be sent to an object of Boolean class? But we know because this is the code of the VM. And we know that the code of the VM is going to send Boolean for sending a true or a false argument, nothing else.
Thank you. That answers my question. I don't, Gilad, you can keep going.
Sorry?
I said, I'm happy for you to keep going. That answered my question. Thank you.
I don't know if I can keep going much longer because I need to go do other stuff, but I might ping Pocho offline about things, but we'll see.
I was looking at the chat to see what the questions were, if there was any. I don't know if Damien is here. He asked, I'm trying to read the question and try to understand what he meant by the question. Give me a sec. I'm not sure with Damien question. I'm not sure what he's asking. If somebody could clarify.
I think I understand what he's saying. Basically, it's another way of getting around this problem of shooting yourself in the foot, right? But one thing you can do is have the subsystem parameterized by these things, so that you can test it against mocks or do different ones or make copies of them, all of which again, yeah, with Newspeak is fairly easy to arrange these things. And he's asking how you deal with this, and to some extent you answered this, right? You have these systems for running a remote thing and manipulating it from the outside, which gives you that effect in a way.
Yeah, well, it's still unsafe, right? So the question is if there's a safer. If the question is if there's a safer way, I would say no. I think that the way in which Sheila answered is the only thing we have, right? We cannot like try it in a safe way, in which, for example, when you're accessing raw memory, it would do something instead of accessing raw memory. You can do it from the remote side and it will crash if it's the wrong thing, but nothing else.
I think that's a fine answer, right? It's so it's not that way you make it. It's not quite self-surgery, right? There's a difference between brain surgery on yourself and brain surgery on someone else, especially if it crashes, right? So that's the best you can do. You still have to do the actual swapping out the brain, but if you can do it on a separate copy, then you're in slightly better shape.
Yeah.
Yeah, we haven't tried that much. I mean, when you have to modify, let's say the GC, it's there are not that much tests. It's a hard thing to test, right? It's like how do you test that the GC is not, or how do you verify that the GC is not running over some random memory? Well, that's are the kind of hard problems. I think it's hard like other systems, not harder, but not easier. You can look at the code. That's a very important thing. You can look at the code. You can try some stuff, but still you're dealing with raw memory, and it's like you lose all your or most of your tools that you used to have in the safe system. You can still try some things and they will be safer, but like if you use the wrong object with the right, like if you have it does not understand, it won't crash or might crash, but you will be able to see the crash, but not much more help than that.
Makes sense.
Okay, guys, I don't know if something else we're just done. I don't know. I think Giovanni had to leave. I'm not sure if there's somebody else to moderate.
Around actually, I don't know. Did he make me a moderator? I don't know if he did because I was late arriving myself. Sorry.
He said something in his message, right? When he left. Where did it go?
Oh, I'm a host. He's
Oh, okay.
There we go.
Yeah, it says Tim can assist. Yes.
There you go. I didn't realize I was at that level. I wasn't when I first logged in, but there we go. Well, I mean, that was a fascinating talk. Thank you for like continuing to power on and cover like so much detail. It's really cool.
Yeah, it was a long talk. I still feel there's much more to tell about it. It was a little bit at some points unstructured, let's say, but if you have any questions, you can just send me an email or whatever. You can find me on the web, find my email address or send me a message somewhere. I will be happy to answer. I don't know. Hope I will be able to show something more in the Smalltalks this year. Won't be to ISAC, won't be going to ISAC, but in the Smalltalks, I think I'm going to show something. So it's a good opportunity. It's going to be in Mar del Plata, was announced this week. So hope to see you there, some of you, and if not, anyway, you can ask by mail, and I will be very happy to answer questions and to share ideas.
Well, this has obviously been recorded, and so it takes a couple of months for Gio to kind of get them transpiled and cut and put up, but he does put them up, so hopefully that generates more questions. And to be honest, just having a forum to like talk about these ideas and get them out there is half the battle. So, you know, the idea is these talks don't have to be perfect. We just enjoy hearing what people are doing and giving you a chance to practice talking about them. So yeah, no, thank you. I mean, it's pretty awesome, actually.
Okay,
Yeah,
well, thank you very much.
what will be the next steps for you to work on UX model?
The next steps are, well, we are plugging the LMR. We are making, we are trying to make all things work as expected, because nowadays, if you try it, you will be able to download it, but still it will feel like you cannot do much or nothing works. So one of the things would be to be able to package it as something that can be downloaded. For example, this kind of generating the JavaScript files. We could generate all the JSONs and everything, and also the transpiled interpreter into a kind of zip file or whatever, so that people could download it and use it. And so there's kind of lots of infrastructure work and making it work as everybody would expect. So I'm trying to dedicate one slot of time for each thing that is missing, one slot for LMR, one slot for JavaScript optimization, one slot for website, and go cycling about that. But if people want to try it and say, hey, look, this thing is not working, that's also useful. So if you want to try it, please do it.
Yeah, I like the approach that you compile or you bootstrap, let's say, a kind of initial virtual machine, and then you are totally inside of the Smalltalk again. But to me, the question is, okay, what kind of Smalltalk will be ending up on top of that?
Yeah, well, I think it will be like any Smalltalk that you are used to, but it's going to be a very small one because it has no IDE. So the IDE is just a very thin layer that lets you connect from the other side, and you connect like this. So you're going to open a server and work with that server, and that's it. But then the server can work natively or with Node.js or in other ways. So it should feel like a traditional Smalltalk, but slimmer. I think that's my idea.
Basically, you could package the whole runtime as a npm package to download, run the web server, and then connect to it. And just
exactly. Yeah, I also want the website part to be like, let's say, apt install website. For Egg, it would be like the same, apt install Egg, and then you just connect it and start doing development. But the idea is not to work in by saving the image, but more in a more, I don't know, trying to save the code and not that much the image, because I think that saving the image sometimes leads you to environments that you cannot repeat afterwards. So it's you get lost in your image or in your images.
You lose them when you refresh the browser.
Yeah.
But just a question regarding the runtime that you bootstrap. If I have seen correctly, then let's say this one doesn't have a meta hierarchy.
Sorry,
So it's
I
just
didn't get
basically
you.
plain Java classes, right? JavaScript classes. The first step of the bootstrap.
Yeah.
You have your egg object and your egg keep object and so on.
Yeah.
So these are just plain JavaScript class files.
These ones are just JavaScript classes and are instantiated by loading the objects from the JSON. I can show you that very quickly. So the loader, Let's see where it is. Oh, here, that was the file I was looking for before. It's the only other one that is still written in JavaScript. It's very short. So it reads the file and it maps the objects to, depending on the type, to slot object, byte object, or small integer. So here you create the instances, right? So if you look at the, if you were to look at the running JavaScript code, you will find only instances of this kind of objects, and then you will find somewhere an instance of the evaluator and an instance of, let's say, the runtime. It's an metacircular runtime that works together with the evaluator to evaluate code. But that's it. So the image is generated from by reading this JSON file and generating the objects from there.
Which was the binary file, right? The kind of the
Yeah.
dictionary.
And we can also, let's say we stop this. One last thing. What will be, where is this? Change. Okay, so I put a breakpoint here. So to load the kernel, opens a file, creates a reader, parses the JSON as data. So you have there this dictionary with objects and exports that we were seeing before. Well, imports aren't going to do anything. And then we just, for each object, it recreates the object. So basically, this recreate looks at the type of the object, which is the first entry here. It would be like the thing at position 0, I guess, and then it just create an object of the different type, the corresponding type, and that's it, right?
That means you
and
will not see these instances then on the. You will only see instances of these three classes on the JavaScript side. So it will be tough to interact with them from the JavaScript. For instance, if
yeah,
you would like to work with JavaScript together.
Yeah, if we do this, let's say we go back to this thing. Let's let it run. And now, for example, so here we have the kernel. I think the kernel is the kernel object. So what's going on here is that this kernel variable is an egg heap object. We can watch that in the debugger. Here. Oh, I don't know why it shows it differently, but here kernel is an egg slot object. So if you tell kernel to string, this is something that is added to the egg slot objects and to the objects of to the JavaScript objects in the glue code. They will ask for the JavaScript print string for them. So you can see that this is of class kernel module, right? And this is kernel. So you can work with the objects. Like you are seeing a low-level representation of the objects. They are not raw memory. They are not high-level objects, but you have something in the middle. It's quite good to be able to look at them, because you can see their slots, right? So, for example, let's say it's a name. So, or I don't know, it's Neil. I don't know what's there, but you can check at the things there.
I wonder if you could map directly to JavaScript itself. For instance,
If you
you
could,
have the possibility there for classes, you have the possibility there for modules.
I'm sorry,
And
I didn't get you.
To map directly to JavaScript.
Oh, okay. Well, no, that's in purpose. I mean, it's like the VM is transpiled to JavaScript, but that comes with a cost because the JavaScript semantics are not the same than the Smalltalk semantics. So you have to be very careful when transpiling to be sure that everything works as expected. Instead, the Smalltalk objects are not transpiled, or the Smalltalk objects of the image, they believe, let's say, that they are working in a Smalltalk environment where everything is Smalltalkish, right? So we are not trying to map Smalltalk to JavaScript, but that's on purpose. I know that, for example,
to stay portable, to stay portable, for sure.
Yeah.
But I wonder what would be the outcome if you would do.
Well, in Pharo, Pharo.js, they do that. So we could ask them, but there are subtle incompatibilities, I think. That would be one of the problems. For example, for does not understand, if I remember correctly, to implement does not understand, you have to add, for each symbol in your image, you have to add a function in object prototype that implements that symbol as it does not understand. So you will have, for example, let's say yourself, right? Or let's, or whatever, foo. You have foo symbol in your system. You have to say object dot foo dot object dot. You have to implement it like this. I don't know. And here it has to call the VM until does not understand. And that for each symbol in the image. So, oh, sorry. So I don't know. These are like trade-offs, right? It's not that something is better than the other. I think it's you choose different things. From the point of view of performance, I think well, the last time we tried, it was like more or less like what Amber was showing. Like I don't know what the performance was, but it was like maybe 100 times slower than native, or I'm not sure if it was 100 or 10 times. I think it was 100. 100 times slower than native, which is a lot, but still it's okay for some code. So if you are not going to do processing, you are not going to do much, maybe it's okay, maybe not. And I have in mind some ideas on how to optimize, but we haven't had time to develop them much more.
So how do you approach what gets loaded?
Sorry?
Like, In terms of the transpiled VM and the image
Mhm.
generate, what's the total size of that?
We can check.
It's a shame Eric's gone because, like, I know he worked on, like, I guess Squeak.js plus a minimal Pharo image. I can't remember what the exact size was, but
So the JavaScript generated is this, so less than 10,000. And there, let's check the handwritten ones. Yeah, in total it's less than 10K.
so that's cool. And then the actual image itself that gets loaded. So because, like,
Yeah.
presumably if you're in a browser, so you download say 10K of
Yeah,
JavaScript.
that's a big thing. So let's see. And especially because it's not
It's
not
not
compressed.
binary, is it? Yeah, it's not. But you could. I mean, I
Yes.
suppose you
So,
could. I guess you could have zip in your image and then unzip it somehow, or I don't know.
so for example, the kernel here is 3 megabytes, a little bit more.
Okay, that's not hard.
Compiler. I guess that you could be able to compress that, and in a way that still you can load it. And the good thing is that you don't have to load everything. You just can load the kernel if you want and your module. So from the point of view of the user is probably going to see, I don't know, the kernel loaded and all the dependencies that the project needs. The developer can load more stuff, but usually that's not a problem. And the IDE is just running somewhere else, so you don't care.
Because I'm thinking like Code Paradise, right? There's the size of Squeak.js. I don't know how big Squeak.js VM is. And then I think from memory, was it like a megabyte, the image? He created a minimal image. So, it was.
The minimal was 200 or so.
Yeah, it was something like that. Yeah, I don't know. It's sort of, so it's reasonably quick to load in a browser or like from a mobile device, but like you're getting to those kind of sizes, aren't you? I mean, and this is like unoptimized in any way, so it's interesting.
Yeah, and actually the kernel,
including the source, or is it just by code stuff?
I think it includes the source. I'm not sure because if you look at the methods, the method objects created, I think they are there, but I'm not sure. Let's check. We can check. How can we check this? I'm not sure how we can check this. Let's try this and interrupt it. Oh, I'm looking for the wrong.
JS image.
Yeah, because this image hasn't loaded the JS part, but let's see here.
Yeah, I guess Squeak.js is 300K, isn't it? About 269 kilobytes, it says. And then his image is 216 kilobytes. So he's kind of got it to, it's like half a meg, I guess. Code Paradise.
He's not giving the source code, he gives the compiled.
Yeah, it's just compiled
methods to it.
Let's see if from here we can get access to some object to check where it has some.
Yeah, the interesting part of Egg is that it has this module system, and if you say, for instance, the kernel is a stable module, you typically do not change the kernel then afterwards, even when it's 3 megabyte. Let's say you can cache it, so you only have to download it one time as a JSON. as a resource. You can have a CDN or whatever to serve it, and then it's then part of the cache already of the browser.
Yeah, here is the source. So if it's like this, I was just looking from one point to the other, one object to the other until I found a method, and it seems to have the code. So I guess that the source has the code. And actually, this is something that should be optimized, I guess. Yeah, when you look at the JSON, any of this, yeah, you won't find any string here because strings,
at the end you will find symbols.
because of Unicode support, the strings are written as a series of an array of numbers, right? So this might be a string.
Yeah.
So the source could be compressed a lot. For example, if the code is, let's say, ASCII, but we haven't tried that.
What will be the approach for, I haven't played with B, but what will be the approach when you say, okay, you have a portable version, because you bootstrap a virtual machine, for instance, in JavaScript, and then you put on top the Smalltalk kernel that you boot. And when you have, let's say, the C++ generated VM, then it boots the same Smalltalk on top. At some point in time, for instance, you would like to go somehow native from the Smalltalk itself. So you would like to have an FFI, for instance, in Pharo, you have the UFFI, and you want to access some DLL or whatever shared object. How do you deal with that? Because then you are not getting portable anymore, because then either you live in the browser where you have no access to DLLs, or you are on a native, let's say, Windows or Linux, and want to use shared libraries.
Well, the thing is that for that, what we plan to do, because we still don't have FFI, right? Because or in the case of JavaScript, our FFI is to the JavaScript world. Our external foreign function is called in JavaScript. But in the case of native, this should be handled by a series of things. First of all, you always have the host, right? So you have some kind of access to primitives or things like that. And then the module system, what I expect to do is to generate not only the kernel, but the like a thin layer for the OS that the loader will load. Imagine that in the case of the CPP, let's say here, I'm just making all this. So let's say we create a folder with the image segments. And here we have some kind of binary, which would be like the kernel.egg image segment, let's say. So besides this, we will have something else like the Linux image segment. So the loader would load the kernel image segment, the Linux image segment would plug these two together, and then you will access them through the host. But the idea is that the modularity is going to give you like the bridge between here and here, right? It's like you access, let's say, file, and well, file might be found here, or maybe file descriptor is going to be found here, something like that. So the system will dynamically load the OS, the corresponding OS image segment.
Reminds me on the approach that Smallscript David once had. So you were able to compile the Smalltalk module into a DLL, run to an executable, But basically, it was just okay. You had the portable executable format, the native operating system, and you just packaged in the Smalltalk classes, and then you used the OS loader to just bring it into memory.
Well, we use that for B. We package the kernel for as a DLL, and but we still use a loader. We used to actually do a system that was completely self-hosted, so you could just write the PAE, point it to the entry point of some special method, and that will run and just be okay with that. So you didn't even need a loader, but it was tricky because sometimes, I don't know, you had to write all the relocations and a lot of things. Instead of that, in the end, we kept the DLL, but we use loader. So the loader basically loads the kernel, the DLL, and jumps to the entry point. And the DLL, the only reason why we are using it is because if you are using a debugger that is like, let's say, EDA debugger or GDB or WinDBG or whatever, if you are looking at the DLL, it will give you information about where the code is and where the things are, because we are adding exports for each method. So each method in the DLL is labeled. And if you generate an image segment with an ad hoc format, then the debugger won't know what it's seeing. So the DLL is for that, but we know how to generate portable executable format. To package an image segment inside that, and we could do the same for Linux if we wanted.
So that's for the demo. This was really cool.
Oh, thank you.
Sorry to ask one more question. So when you've got all of this running and it's running on the web, you've got your JavaScript VM running on the web. What do you do with the code that you write? You mentioned tonal format, but like how do you persist code at this point? Is this like some interface to Git or something, or what's the next step of that bit?
Well, that's a problem for a website, I think. No, but yeah, if a website has methods or mechanisms to save the code, right? For example, well, in this case you cannot see, but here you probably can. If you change a method in Pharo, let's check if this works. Yeah, you have it here. So you can basically, for example, download them, right? And I think there are better ways to save the code that website allows, but I'm not sure how they work. But anyway,
so you download in tonal format and you can upload in tonal format, I guess. Is that the current method?
Yeah, exactly. So what you could do, because in the end you are just running a server, and so if we look here, the website, the example server, the last part of it is starting a new website server, which is in a folder here. So this is a website backend that knows how to interpret, for example, egg objects to answer questions. Here is the API. So, and here is the server, right? So the server knows how to respond to each kind of request.
Right.
And so if you implement the correct parts of the API, which I haven't, then you can make it, for example, save code somewhere in the file system. Because this one in particular is running on Node.js, so you have access to the file system. If you wanted you could be able to write the changes that you have in the image to the file system.
Right.
But still, that wouldn't be get saved to the kernel.json, right? It's a different thing.
Yeah.
We usually, and the same for B, we are not used to save the image. We usually just save changes, and if those changes happen to be in the kernel, we will strap again. If they are in a library, usually what we do is to throw away the library cache, which has image segments which are already compiled. So basically, loading a library is very fast because usually you have it cached as an image segment. But if that code changes, you throw away the image segment and you generate it again. And so the next time you load it, it's going to be very fast.
Okay.
So it's like the image is assembled dynamically from binary files.
So I suppose I'm just trying to imagine if you had this web UI and you've got your server and your server is running somewhere, you'd have to write some other mechanism to persist things in the more traditional, like, if you want to not download stuff and you want to like save every change, it's a case of implementing some mechanism for that, whether it serves it locally or whether you automatically store it in Git somehow as a.
Exactly. I mean, for example, in B, we just have this object, which is like the B image. And you can tell it just, let's say, save image. And so if you send this message, it will save the image, right? So if we had something similar in Egg, or well, in Smalltalk, this is just standard, right? You just send the correct message and it will save the image. If you want to do that, and if you want to save the code instead of an image in tonal files, again, and this is something interesting because here, when you see the code that generates the JSON, what that code does is to generate an image in Pharo, and after generating the image in Pharo, it sends that virtual image a message that tells it to write itself as a JSON file.
Right.
So what you see, oh, this is not the XJS. Let's check some XJS. It does something like this. It takes some module and tells it to write an image segment. And when you go and look at that code, it's in the virtual image that has been loaded. Actually, it's an extension to the module class. It generates this builder object, then sends it to build the closure of all the objects referenced by this module, but that are inside that module and not outside.
Okay.
And then it takes a writer and writes that as a JSON file.
Yeah.
And we have been doing this for B for a long time, and we know it works. With modules, I think it works a little bit better because you have better boundaries, but both work. And one last thing is that after this writes the image, what it returns is just a string because the virtual image doesn't know how to write to files. So what you see after doing this is that it returns some JSON And here the host is the one that creates the file, truncates it, and writes it as a string.
But I guess what's written out there is what an image segment as opposed, and the image segment is that binary encoded
Yes.
source
Yes,
format. It's not great for version control, is it? That kind of mechanism.
Yeah, it's horrible it's not for controversial at all.
But you could have a different kind of builder, like to build it a different way to get it out.
Yeah. Yeah.
Left as an exercise to the reader, right?
I don't know if it would be the best thing to do. It's like having saving the DLS that you build. You can have different compilers building different things from the same source code. But yeah, at least it could save like the some meta information about what's the version from which this image segment was generated and what was loaded or what was not.
I mean, I guess it's trying to escape the confines of the file system, because like in a web world, if you're running this on the web, you don't really think about files. It's more like persistence services, isn't it? It's like how to. But I mean, I guess you could have something that takes the builder
more or less
and deconstructs it and stores it somehow. If that is a different service, that
It's not just that, because you could have a file system implemented as accessing URLs in the web.
Yeah.
But the thing is that with this, you don't have to compile the source while loading. So you don't even have to load the compiler.
Yeah.
If you want to load your library, you just generate the image segment, and then the client can just load that image segment without even loading the compiler. It's much faster and smaller.
Yeah. Okay, I see what you mean. To get it in your image, that's a very efficient format.
Yeah.
To diff it, you want some other mechanism, but maybe that's a different. Yeah. Okay.
Yeah, I see those image segments as a very disposable files. So if you find that they are not what you expected, you throw them away and start again fresh from the source.
Which is the other mechanism to download the source, right? Is that other button that you were showing me? Yeah. Okay.
It is a difference between runtime and development time. For development, you need the source code for, let's say, deployment. Say in the final application, you might not need to have the access to the source code. So you might just generate the binary representation in the JSON.
Yeah, we could even strip this JSON from the source code if we wanted.
I suppose the other thing that skirts around, of course, is, I mean, I guess the modules have some concept of dependencies, but an application is composed of like lots of modules. So like you haven't got the whole Metacircular thing to, how do you load a whole application? That's still the next project to do, right?
Yes. Yeah. We have to see how to deal with that. Like, what is an application? What are the dependencies of a proper application? Yeah. Depending on how you want to work, it's.
Yeah. And you said you do all the name bindings lake bound because of the module system, because you could import dynamically. Let's say if you have name clashes, or you import a name binding on the module, and you define on the module, okay, for instance, I require the class object from kernel, and this refers to this object. But if I have another module, I could say, okay, I have an own object class, same name but a different binding.
Yeah.
But is there no optimization to say, okay, for everything that is inside of the same module that you do not lake bound because you know the name? But
the thing is that the first time the code is run, it's optimized with the proper result of the lookup, and then it doesn't care anymore. So I don't think it would be a real problem. If you look at the VM, it caches every result of a message lookup, and then if actually if the name changes, I think it precompiles the code the next time it runs, because it generates something that. So let's see. The compile method has in Egg has these bytecodes, and also has this optimized code, right? So these are the three codes. I have to migrate the names, but this is what usually are the bytecodes. And this thing is actually the executable code. It's called optimized code, but it's an object that has been generated from these three codes, and that already
This is the runtime bytecode.
Yeah, already has the objects required for caching the names, and the names there, when the VM executes for the first time, it finds that the cache is empty, so it does the lookup. But then in the next time, the only extra processing that it has to do is to check if the cache is empty, and if the cache is not empty, it uses that cache. And the thing is that in the future, what's going to happen is that this is going to become a multi-stage compiled VM, right? So it's like this. The first time you execute it, it does that. It caches the thing, and then uses that cache. But after executing the method for some time, if it finds it's a hot method, then it's going to generate native code for that. And that native code is going to not even check the cache, because if the code hasn't been discarded, it's because it's still up to date. And if it's still up to date, the name still matches what it matched before. So it's going to be completely free, no cost.
Yeah.
Interesting. Yeah.
This is what I think what is required, because many of the regular models do not have that. You might have namespaces. The real module system with a bound possibility. This is really neat, especially when you would like to have a system where you have dependencies and possibly load the dependencies then web-based from other sources.
Maybe I get what you mean. I don't know if you mean this, but I can try, or at least I'm imagining a situation. Let's say in your namespace A, you invalidate some name.
Yeah.
So you don't want to invalidate all the code of all the modules, but only in that namespace, the code in that namespace. Is that what you meant?
Yeah, and you know from the imports which one to invalidate.
Yeah. Well, it's
because the other ones, if you think of a module, you have, say, certain classes that are like a private classes, because you know their name. And their name is typically, let's say, bound only first of all to the module itself. So if you have, for instance, two classes inside of the same module, one using the other, then you know the name, and you do not need to have the late bound because you have it right away. Until it's changed.
I think it's possible, but it would be tricky, because it's something that you can find names in places where you didn't expect. Like I don't know, I'm not sure how, but
The other thing is that I was thinking, because I was experimenting with other topics, is okay, why is the name thing that you need?
Mhm.
Because if you
Yeah.
think about, for instance, I remember a story about someone told me back many years ago about a visual log system that had been translated to French because they didn't like the English version names, so they really renamed every class, even the base classes, into French language, which was, let's say, okay, you can do that, but this will be shooting yourself in the foot. But the interesting part is when you think as the name of the class only as a kind of, okay, it's just another property. It can change at any time, and you should not use the name, but you should use something stable. For instance, every class could be identified. How could it be identified uniquely? This is what the name is, what the name symbol is at the moment in every small talk. In every small talk, the name is what is the unique, let's say, key to you know, if I tell you object or if I tell you Boolean, you know, okay, it's that class. Huh? Even when you have a different small talk, but then it's a different class because it has a different methods and other things. And if you think of a multi-small talk where you could import, let's say, Visual Works code and run Visual H code and run GUI's code or whatever, everything on the same VM, you will have to deal with two or three or five object classes. And you have to think about, okay, what is really the unique identity? In a database, you would use a key. And if you think about, okay, what is unique in the world of IT? Okay, it's unique identifiers. So what Windows uses the UUIDs because they are unique in time. You cannot generate a second UUID on a different computer. So if you would use, instead of the name, using UUID to identify the identity of a class, and the name would just be a property, you could just use the name, but what you bound to will be the internally would be the UUID of the class. You get my point?
Yeah. Yeah.
Because then you can rename
eh,
the object
yeah,
identity will be the same.
it gives me many things to think about. One of the things that I have many things to comment about that. So first of all, just an implementation detail. For example, our module system is flawed in this way. When you import something into your namespace, it becomes visible from the outside. So because we are using the same dictionary for imports than for exporting or whatever. So if I import something from the kernel, then the one that wants to import from me is going to see what I imported from kernel. We should use two separate dictionaries for that, like a private thing for our names, public thing for what we want to export. But it's not a problem for now for us, so we don't care. That's one thing. Other thing is that we want to have this kind of aliasing, because what I want to do, and that's one other thing that I wanted to change from egg, from B to egg, and from all other small talk, was something that some people will think it's horrible, but I want to call this list. So that's a huge change. And what I want to do is to have aliasing so that you can still say order collection and it will find list because it's in the namespace imported as list. And you could also import list as order collection if you wanted, so that you can your compatibility.
Latest Pharo has something like that. Because
sorry?
there is a possibility in Pharo, in the latest Pharo version, there's something like that as well. Because for instance, you could use that for deprecation. For instance, you want to deprecate an old name of a class and you would like to introduce a new name for the same class.
Yes, good.
There are many use cases for such a thing.
Yeah. And one last thing that I wanted to say about all that you mentioned about the UID is that one other thing I wanted to explore someday was, so let's say this is a working Smalltalk image. what if I wanted to say import quiz or import Pharo, right? And make that like a module, and you have object there, and it's their object. It's interesting. I guess nothing would work, but still. Or maybe you could import some part of the system.
The question you have to ask yourself is, why do we have the name object? Because we are, as humans, not very good in interpreting numbers or UUIDs. So we call it object, and it's, for us it's better than a binary. Let's say it's better to read text, textual representation. So if we speak about object or about the class person, we speak about person. But the problem is, and this is, let's say, what is better solved in Java, because they have namespaces, so everybody can have its own unique person class in its own namespace, because they use these com dot whatever dot whatever.
Yeah,
person.
this notation.
You already, by having this separation, you already take care that there are no collisions. And
Yeah.
you still keep you still keep it human readable. But it doesn't help you nonetheless with these migrations. For instance, for instance, when you have when is person class not anymore the old person class? If you think about versioning of classes, for instance, if you change an API too often on a person class, then it's not the same. So it will break your API when you call it, especially in a module system when you load it. So the question is, when do you give up this identity? But to identify uniquely, and in the past, it was never done in smaller systems, say to assign a UUID to a Smalltalk class, for instance, because of space savings. But if you say, okay, you identify the classes with an UUID instead of a name, and the name is just how it's currently called, or how it is represented in your text, so when you write the code, and you separate this could give you possibly a new way also for these references, and keeping these references and changing names at will, because then you do not need to have these late bound.
Folks, I'm sorry, but
Yeah.
I will have to leave.
Yeah, no, it's been
Me as well.
we've kept you a long time. Thank you.
Thanks a lot.
It's already very dark here. Yes, you can see.
Right.
But it's been great to have this conversation. So
Yeah, we really appreciate your time. Thank you.
yeah, thank you too. Thank you too. So have a nice rest of the evening or rest of the day. It's quite late, I guess. Bye bye.
Thank you. Right.
Sending greetings to the other part of the world. Thank you. Bye.
Bye bye.